Okay, so one announcement, as I mentioned on in an announcement a few days ago, for those of you who've been at the university for a little while, the course evaluations have generally been on paper, but I don't know if every department has switched over yet, but at least statistics is switching over to online evaluations. So I think, I'm actually forgetting when the last day you can do them is. I think it might be like the 13th or something, but please do go ahead and fill those out. And particularly since the course has changed somewhat since last year, and it's a bigger course than it has been in the past, it'll be helpful to me to have your feedback from those evaluations. Okay, so we left off talking about integration. Any questions from last time? Okay, so one of the ideas I was drawing out was that a lot of the different methods of integration, some of which you've seen before, can be written in this form here, which is basically a sum over intervals, and then you have some approximation in each of the individual intervals. So if you just monkey around a little bit algebraically, you can see that the Riemann approach or the trapezoidal rule or a Simpson's rule can all be written in this form where we're doing the approximation and the interval in a different form depending on which of these methods we're considering. And then I mentioned that when people study these methods and think about how much error there is in doing the integrals, then they're often quantified in terms of the length of the interval. So I guess this would presume in these various cases that we're talking about equal length intervals, and we'll talk about adaptive methods that don't have equal length intervals in a little bit. But that something like trapezoid rule gives an error order of h squared, and Simpson's rule gives an error order of h to the fourth. So rather better in terms of the amount of error. But as a sort of a theme that we've seen other times, we can get more accuracy or a better answer often by doing more calculation, but there's obviously a price to be paid in terms of how long it takes to do the computation. So in some sense, many of our quantifications of how accurate any given calculation is has to be done in terms of some unit of currency, and the currency is often that we think about how long it takes, either how long it takes, or in some cases that could be expressed in terms of how many evaluations of a function have to happen. So if you think about doing the trapezoid rule versus doing Simpson's rule, well, in this case, for each interval, we have two function evaluations that have to be made, except these are the endpoints of the interval, so if we then do the next one, well, we've already done the calculation for one end of the interval. So in this case, it looks like we'd only have to do one function evaluation for each of the intervals. But then if I look at this, well, I have to do twice as many calculations here, because I have to do the beginning of the interval, the midpoint of the interval, and then for the next interval, well, this sort of comes for free because I'll have done this for doing the beginning of the next interval. But this would then be twice as many calculations as that would be. So you have to think about, well, I'm gaining, in this case, I'm gaining quite a bit in terms of the improvement in my error, and the price that I pay is that I'm having to do twice as many function evaluations. So depending on how costly those function evaluations are, that may or may not be a big burden. Okay, so there's actually sort of a clever way that I'll mention briefly to get a higher order error, or get a smaller error, so get a higher order in this h, while basically saving some function evaluations. So the idea is sort of as follows, and this idea of sort of killing off the error terms sort of comes up in other contexts in statistics as well, so it might be something that you see in more of a statistical context at some point as well. So the idea is that, suppose I have the trapezoidal rule, and I have that the error is my estimate of the integral, which I'm going to call t hat of h, and that's going to be a function of the interval size, minus the true value of the integral that I'll call t, is order of h squared. So we could write that, for example, as c1 times h squared. And it turns out the next terms look like this. They're order of h to the fourth. So I haven't derived that here, and I don't have it in the notes, but that's a result that folks have developed. So the idea is that if we're clever, we can basically take the trapezoidal rule and apply it twice, and then do a clever calculation, which is just a very simple arithmetic calculation. And that's basically going to give us something where the error is order of h to the fourth, which is basically what Simpson's rule is. So if we also did t hat of h over 2, well, that will again, we're going to subtract off t. And that error is now, if I'm using h over 2 in place of the h's, that's now going to be c1 h squared over 4, plus this is still going to be order of h to the 4 because I've just got a multiplicative constant here. So it's still the same order in terms of the h to the 4th. Okay, so then the idea is, well, okay, let me just rearrange this a little bit and say, okay, t hat of h, if I just make this equals and move t to the other side, is just going to be this. Okay. So now the way that somebody, whoever it was who came up with this, which I guess should be obvious now that I've met, since this is presumably whoever came up with this was named Romberg. So if we take 4 times this guy minus this guy over 3, well, what do we get? Well, we get 4 times this whole thing, which is 4t plus 4c1 h squared plus something that's order of h to the 4th still, because I'm just multiplying by a constant again. And then I'm going to subtract off, wait, did I do that wrong? Sorry, 4 times t hat of h over 2. So that would be 4t plus 4c1. Oh, I did, okay, right. Okay, so I'm taking 4 times this minus this guy. So minus t plus c1 h squared plus order of h to the 4. And then I'm dividing by 3. Okay, so what do I get here? I get 3t, and then the 4c1h squared is going to cancel out. So that error, basically the error term that's order of h squared cancels out because I've done this sort of clever trick here. And then I've just got 2 order of h to the 4th terms that I'm subtracting, so that the result of that is still going to be order of h to the 4th. So now I've got 3t plus order of h to the 4th over 3, and that's equal to t plus that's still going to be order of h to the 4th. Okay, so if we use this, if we use an estimate that's this linear combination of these two guys, then we get that that's equal to the true value, which is what we want, plus an error term, a difference that's order of h to the 4th. So that basically, this is actually, if you sort of work through the details, it's basically giving a Simpson's rule with intervals of h over 2. But if you also sort of work through what are the exact function evaluations I need to do in coming up with, in doing this calculation and doing this calculation, what you'll see is that it only takes 2n evaluations, where n is the number of intervals. Whereas if you actually did Simpson's rule with h over 2 as the interval length, you'd have to do 4n function evaluations. And you could, if you're interested in this, you could, the Givens and Pating book actually sort of shows how you can sort of iterate this and get even higher order approximations by doing strategies like that. So I think sort of the take-home message here is, again, this idea that we're going to rely on the computer to be fast and do calculations for us, but there are some benefits in being clever and using good algorithms that we then implement on the computer, and not just try and sort of rely on brute force. And I guess the other is this sort of idea of trade-off between how accurate a calculation we do versus how much calculation we have to do to get that degree of accuracy. Okay, so any questions about that? Yeah, Dustin.
There's an error in your arithmetic on the.
Okay, that's entirely possible.
Because you have like the 4c1h squared. I think it should just be c1h squared. That way it will cancel out correctly.
Oh, right. Sorry. Okay. So yeah. So I was doing 4 times this, so that's 4t plus c1h squared. Okay. So I guess I did when I was writing this out. I think I was multiplying 4 times here when I should have been multiplying 4 times here. Yeah. Thanks. Okay. Okay, right. So yeah, this is sort of the reasoning to the conclusion I wanted. Like I was sort of not seeing the 4 when I did the subtraction. Okay, so those two terms cancel. All right, any other questions or comments? Okay, so that's so these methods can be quite effective. It turns out that there's another strategy that's often used, and this is actually what gets used, or a version of this is what gets used in R in the integrate function, which is to no longer be following this strategy of having equal length intervals, but to actually try and cleverly choose where to do the function evaluations in a way that's not in this sort of equal intervals and then exactly placing the nodes in these particular spots that are the same, relatively speaking, in each of the intervals. So there's this idea that's called Gaussian quadrature. Seems like Gauss was involved in like 73 different things that come up in different contexts in this course, which is if you can express your integral in this term as an expected value with respect to some probability density u, then Gaussian quadrature basically approximates that integral as a sum here, where you're basically cleverly choosing what are the xi points at which you do the evaluation and how to do the weighting. So it gets sort of involved, and it involves understanding these things called orthogonal polynomials, so it's sort of more than I thought we had time to go into. You also need to have the existence of moments of the density for this to work. But the sort of take-home message from this is that as long as the function f is smooth, that you'll generally get a good estimate of the integral from using Gaussian quadrature. And in fact, if the function that you were integrating is actually a polynomial of degree 2m plus 1 or less, and this is m being the number of points at which or m plus 1 being the number of points at which we're doing the function evaluation, you can actually get an exact estimate of the integral. So if you're sort of looking around and you know what integration problem you have and you know that it's smooth, then you have a good idea that Gaussian quadrature will work pretty well. On the other hand, if you knew that your function was not particularly smooth and you didn't think it could be very well approximated by a polynomial of this order, then it might be a better strategy to use, say, the Romberg quadrature, or one of the techniques that we mentioned from the previous page of the slides. So I don't think, obviously that was a very high level. I don't think I want to say too much more about that, except just to sort of have you guys have seen this and sort of have this idea that there are sort of trade-offs involved in which method you might choose, depending on what the characteristics are of the function that you're trying to integrate. And then sort of more generally, there are a variety of adaptive quadrature methods that are basically choosing the interval lengths and exactly what intervals you use based on the behavior of the function. You can sort of think that would make some intuitive sense in that if I know that my function, maybe my function looks like this, well, it's probably not worth a lot of time and effort to put really, really fine gradations of intervals over here because this is very smooth, and it might work to just have some small number of intervals over here. But if I do that here, that's probably not going to do a very good job because of the behavior of the function. So here I presumably would want to place my intervals much more finely in terms of doing the approximation. So there are sort of a variety of techniques that do this in this adaptive fashion. And if you hear the term adaptive quadrature, this is sort of the basic story of what's going on there. And then again, sort of the reason for doing this again is this idea of a trade-off with how much computation you have to do. You don't want to waste a lot of computation in this part of the function. Okay, so one of the main things I want to highlight here in this unit is what happens when you try and use quadrature in higher dimensions. So I mentioned at the beginning of the unit last time that when we do Monte Carlo approximations to integrals, when we can put them in the form of an expected value, that actually scales well with dimension. It's not all particularly accurate relative to the number of calculations you have to do it, but it scales really well with dimensionality. Whereas quadrature scales really, really poorly with dimensionality. So what I'd like to do is sort of walk through the logic of why that is, just to sort of hit that point home here. Okay, so we've seen that in one dimension, basically the error can be quantified if we're back in sort of the simple situation of having equally spaced intervals. The error can be quantified in terms of the length of the interval. So if we use smaller and smaller intervals, we're going to get higher and higher estimates of the integral. Again, there's going to be a numerical precision issue. If we get h so small that we're approaching some of the limits of what we can do in terms of doing calculations like on a computer, then you could sort of work through what calculations am I doing, and if h is really, really small, am I going to end up with things like catastrophic cancellation and other types of issues from numerical inaccuracies. So you can't take h, too small because of those numerical issues, but up to some point you can just keep decreasing h. So that's going to involve doing more and more function evaluations as you try and get increased accuracy. So if we think about the number of evaluations, that's often going to be something like the length of the interval that we're looking at divided by h. Or equivalently, the interval size is equal to the length of the interval divided by the number of intervals divided by the number of intervals that we've got. Okay, so that tells us that we've got, we've already seen that oftentimes we can write down the error in doing the integral as order of h to some power q, depending on what the method is. So this would be a 2 if we were doing the trapezoidal rule, it would be a 4 if we're doing Simpson's rule, et cetera, et cetera. So this also tells us that since n is proportional to 1 over h, this is going to be order of n to the 1 over q. Wait. Sorry, n to the minus cube, sorry. I was getting confused with the dimensionality, which is going to come in a second. Okay, so now the question is, well, what happens as we go to higher dimensions? So suppose that we are working in 2 dimensions, and you can basically come up with methods that are essentially what we've already talked about, except now we've got to do intervals in each of the dimensions. So instead of dividing things up into little slices, into little intervals, we're going to divide up into little boxes. And then we're going to, for each of the boxes, we're going to approximate the integral over the box in the same sort of manner to what we did when we were approximating the integral over the interval. So it turns out when people works through the accuracy of doing these numerical estimates of integrals in this context, you basically still have that the error is order of h to the q, where h is now the size of one side of basically of one dimension of this little box. So we could then, we can think about extending this to 3 dimensions, 4 dimensions, and the story is the same. But it's still going to be order h to the q, where h is basically the length of the hypercube in one of the dimensions, however many dimensions of a hypercube that we're talking about. Okay, but the problem is, so that's fine. I mean, that seems encouraging that we can still express it in this way. But the problem is, if I now think about how many function evaluations I have to do, I'm basically now doing n to the d different evaluations. So if I had to do n evaluations, suppose I was doing the trapezoidal rule, I would have had to do n evaluations if I were working in 1 dimension. But now I have to do n squared evaluations because I'm basically doing an evaluation at each of the grid points in this grid in 2 dimensions. So I basically have to do n to the d different evaluations in order to get my h to the q error in this case. Okay, so what that tells us is, okay, in terms of if we now try and go to higher dimensions, basically relative to what I have before, if I sort of instead of scaling up n relative to d, if I have a fixed n, and I think about what happens as I scale up in terms of sort of the effective size relative to what I had in 1 dimension, now what I'm going to have is I'm going to have order n to the 1 over d to the minus q. So, for example, if I did 25 if I had n equals 25 in one dimension, well, now in two dimensions, if I still fix the number of evaluations I have to do, that's equivalent basically to doing a grid where the spacing is 5 in each dimension when I'm working in two dimensions. So I've got to take my original n, which in this concrete example would have been 25, and now it's going to be like I have 5 to the minus q instead of 25 to the minus q if I'm working in d dimensions. So that is sort of based, it's not too complicated. That's sort of the basic story here is that the effective sample size I have, if I have a certain budget for doing computation, let's say I can do 25, that's, then I get whatever, then I get, n to the minus q. So in one dimension I get n to the minus q. In two dimensions I get n to the 1/2 to the minus q. In three dimensions I get n to the 1/3 to the minus q. And so things are getting progressively worse as I increase the dimensionality. And since we're working with these powers, it doesn't take very long for things to go very poor, for things to go to get really bad. So for example, suppose I have the computational budget to do 1,000 function evaluations, and I'm working in 10 dimensions, well, 1,000 to the 1/10 is basically 2. So instead of, if I were working in a one-dimensional problem, I'm doing 1,000 interval, that's pretty good. I'm probably getting a pretty accurate estimate of the integral. But that's equivalent to basically doing 2 function evaluations in each of the 10 dimensions and then doing this 10-dimensional, basically this sort of a 10-dimensional grid, but where I've only got 2 points along each of the axes. So you might expect then, as we would sort of guess, then the error in doing that numerical integral in 10 dimension is going to be really, really large. Another way of putting that is we're going to need to increase the number of computations we have to do to a really high degree. We're going to have to do a lot more computation to get any sort of accurate estimate. Okay, so that's basically sort of the cursive dimensionality in this particular kind of problem. And then the other thing I'll point out here is how this relates to the Monte Carlo estimator. So remember, when we had our Monte Carlo estimator, remember we were approximating the expectation of, under some distribution f for the random variable x of h of x. We were saying that was approximately equal to draw xi m different times from the distribution f and compute this average, and that's our Monte Carlo estimator of the expected value. Well, let me change this m. This was the I used m when I was talking about this before, so I wanted to use that notation here. But let's change this now to n so that it matches up with what we have here. And if you recall, the variance of this estimator was 1 over n times the variance of h of x. Okay, so this is just the usual variance of an average. Okay. So if I now think of it in terms of the standard error of the estimator, and that's basically going to put it in terms of the same scale as we had over here, this is going to be 1 over n to the 1/2, so n to the minus 1/2. And so basically, the thing to notice here is, when we're sort of ignoring the constants, we know that those constants will come into play as well. But in terms of how it scales with dimension, there's no term for dimension in here, so d doesn't enter into here. So if we have one-dimensional quadrature, in general, doing one-dimensional quadrature is going to be more accurate by doing it using these quadrature methods than it is if we use a Monte Carlo estimate. But as we scale up, as we try and scale up in terms of doing quadrature, we're going to lose accuracy very quickly as we increase dimensionality. And this estimator is not going to be affected by that. The Monte Carlo estimator is not going to be affected by that, that cursive dimensionality. Sorry, I just meant to say order of n to the minus 1/2 here. Okay, so are there any questions about that? Okay, so it turns out if you look in the documentation for the integrate function in R, it's actually sort of combining the idea of doing adaptive quadrature, of sort of adapting these intervals to the function with this idea of Gaussian quadrature. And it gets somewhat complicated exactly what it's doing, but that's sort of the basic story of what's going on behind the scenes. And so you would expect that this would be pretty good with smooth functions, and that you might have some difficulties if you have less smooth functions by the reasoning that we've already discussed. So just to give an example of doing this in R, and that you do want to sort of keep your wits about you and make sure that the answer you get makes some sense. So we could, for example, what integrate is going to ask for is that you give it a function, and that function has to be a vectorized function that will take as its first argument a vector and be able to spit back a vector of the function evaluations of the function evaluated at the points in the input vector. So we want to give it some function. We want it to have some f of x where x can be a vector, and the result is going to be f evaluated at each of the values in the vector x. And then the next two arguments are the lower endpoint and the upper endpoint of where we want to do where we want to calculate the integral. And you can give it minus infinity and plus infinity, so it will work with unbounded domains. And then anything after that is just a ... argument in R that allows you to pass additional arguments into the actual function. So in this case, this is going to be the mean and the standard deviation of d norm. And so what integrate does is it takes anything that comes after here and just passes that along to the actual function that is being used to do the calculations. So we could, obviously we know that the integral of the normal density is just 1, but we can do this numerically and see that it does indeed give us 1 back. And as I said before, it gives us some idea of what it thinks is an estimate of the error, and I don't know exactly how it's doing that, but I think it might be by sort of doing a couple different methods with different degrees of accuracy. And we can see that if we make this, if we keep concentrating the normal distribution even more, it's still able to do this integral, and we have a pretty small standard deviation of 0.001. But at some point, it gets so small, and now we've got this function, this density or this function, which in this case happens to be a density, it's really acting sort of basically like a spike at this point. Once that standard deviation gets really small, that this actually fails, and in fact it fails in a way that's in some sense sort of catastrophic, in that it doesn't really warn us that it's failing, which is sort of the worst kind of failure of all. It says, oh, the answer is 0 with absolute error less than 0. Well, maybe this should give you a warning. Maybe this should make you pause. I'm not sure. But obviously this is quite far off from the actual answer, and we don't get any particularly helpful information back from R that something has gone wrong. So I think sort of another lesson in whenever you're doing calculations, you want to sort of at least have some general ballpark sense of what the right answer is, and that the answer that you get out from doing the calculation matches what your sort of rough sense of the problem is. And if you get something different, then that's a good sign that you should go and look into it more carefully rather than just blindly trusting the result of the calculation that you've done. Okay. So I guess I'll say a couple more brief things. If we go back to the notes, I also have this comment about singularities. So another thing that can cause difficulties is if we have a function that has a singularity. So for example, if we have the function 1 over the square root of x, so that function is going to look something like this, and it's shooting off to infinity here. So it turns out that if you can mathematically do this integral from 0 up to some upper bound here. And the reason is that this is not going up so fast that it's not integrable. So you can actually integrate this even though it is going off to infinity. But these sort of singularities may cause problems in doing numerical integrals. So there are various tricks if you run across this. I don't think it's worth going into a lot of details because this may not be something you run across very often. But you can do things like, so for example, if this is the integral you're interested in doing, that involves a singularity because that's just exp of x multiplied by this function here, which has this difficulty here. So you can do things like a change of variables. So if you change variables and let u equals square root of x, this sort of goes back to your first semester of calculus. You need to do the Jacobian of the transformation, and then rewrite the integral as this, and this is something that doesn't have the singularity in it, and so that you could then, assuming that you couldn't do that in closed form, that you could then plug in and do as a numerical estimate of the integral. And then there are some mathematical tricks. It turns out that for a problem like this, you can actually do something called subtracting off the singularity. And that's where you can basically rewrite this original one as this, where you subtract off minus 1 over square root of x and then add it on again and do the integral as the sum of those two integrals. And in this case, you could do this piece in closed form, and then you could use numerical integration to do that piece. So there are a variety of sort of different strategies that you can use when you get some of these tricky situations. And then I just show here that it actually turns out that integrate is actually able to handle this function directly, so I'm not quite sure. So it doesn't seem like the singularity in this case causes problems in any event. But okay, so any questions or comments? Okay, and then the last thing I was going to mention is just that like I said with doing differentiation, is that rather than trying to rely on doing differentiation by hand, it's often a good idea to try and do it using a computer program. Mathematica and Maple are particularly good at symbolic differentiation. They're also good at symbolic integration. So if you have a tricky problem that either you don't want to integrate by hand because you think you might make a mistake, or you don't know how to integrate it by hand, but you think, well, maybe it's possible to actually do this integral, you could actually just plug those, just throw those into Mathematica or Maple and see if they can do the integrals. And the form in Mathematica takes a form something like this. You give it a function, and then you tell it what are the symbols that you want to do the integration with respect to. And you'll often be able to get a nice answer as a result of that. Okay, so that's sort of a quick whirlwind tour through integration and differentiation. Any questions before I switch to graphics? Okay, so as I mentioned last time, this unit has some 30-odd pages, and in some ways is sort of just a brain dump from me to give you some useful material that might be useful to you down the road. So we're just going to hit some of the highlights here, and one of the things I want to focus on is just sort of talking through some of the principles of what makes for a good graphic, and what are some of the pitfalls that you should try and avoid when you're creating graphics. So I thought what we could do as a start, as sort of a warm-up, is just to look at an example of a graphic that this is actually from a website that is sort of meant to be showing examples of good design and good graphics. And I think as we talk through this, we'll see that there are some issues with this graphic. So what I'd like to do is just sort of give you a very quick introduction to what this graphic is doing, have you guys look at this for a few minutes and see what you think about are the good things and bad things about this graphic, and then we can see what we can come up with as we discuss it. So I'm not sure how to, turns out this is not scaling as well as I was hoping it would. So maybe we can look at it in sort of two pieces so it's big enough to see. So this is supposed to be a graphic that's saying something about the male-female split in terms of who uses different websites. So it's saying something about some websites tend to be more used by women and some more used by men and some that are more or less equally used. And so it has these different websites, and then it has these little people that are supposed to indicate something about the proportion of men versus women. And then it has this percentage, which I think is the percentage of users. So this column here is something about that there are some number of million more monthly female versus male visitors. So that's in some absolute estimate of how many more women than men there are who use, or men than women in one of these two cases, who use the website. And then this is the gender percentage of people who visit the website. So, whoops. So we see down here that that this says the total is there are 99 million more monthly female visitors overall to these various websites. And then down here it says rounded U.S. gender figures and worldwide traffic figures. So it looks like this column has something to do with U.S. and this column has something to do with international traffic. And then you can see that it's doing this ordering of the different websites. So maybe I'll leave it like this. So take a few minutes and look at this and see what you think about what you like about it, what you think is clear, what you think is unclear, and how you might either think about change if you were going to change this around and redo this graphic yourself, what you might do. Alex, you have a question?
The first column numbers is a percentage, right? The second is
Yeah, I believe this is a percentage, right? And then this is an absolute millions of people value here. So yeah, okay, so take a look. And if you have questions, maybe at this point let's hold the questions, because in part the questions are going to may indicate sort of a lack of clarity in the graphic, and is something that we should talk about. And as you're thinking about things that are clear or unclear, one of the principles in which when we're designing a figure or graphic or a table for that matter is we want it to be something where the reader can look at it and understand what's going on without having to read a lot of fine print and sort of trying to do very fine interpretation of sort of what's going on. So it should be, the idea is that this should be clear, sort of what it's showing without having to think all that hard about it. Maybe I'll scroll down here and see if anybody wants to look at this stuff down here, if any of that is then helpful. All right, so what do people think? What jumps out at them as things you either like or don't like, or things that you weren't clear what it was doing here? Yeah, Jason.
So it's not clear why the cutoff for inequality is 53%.
Okay.
So we don't know whether 4 squares is matriarchy or patriarchy.
Right. Okay. So it looks like there's some cutoff between 52 and 53. It looks like where they decide to group into equality and matriarchy or patriarchy. But sort of what's the criteria that they decided about that by? Sarah.
Seems like the graphics is showing the number of people that are over that cutoff is pretty redundant with the percentage column.
Okay, so it looks like what this means, and I don't think it's ever actually stated what these little people represent, which is maybe a downside of the figure as well. It looks like that there's a one person up there under ORCUT because that's 51%, which is 1 percentage point more than the 50%. Actually, before we get to that, let me go back to Jason's point, which is what are some different ways that you could think about doing this grouping into equality, matriarchy, and patriarchy? Like, why do you think they chose 52.5% or whatever it was as the cutoff? Jeff?
maybe what their survey decided was statistically significant. Yeah, if they just did a basic survey or some sort of usage statistics.
Yeah, so maybe there's some statistical uncertainty measure in here. Maybe they're doing the grouping based on that. It's sort of unclear. Maybe they just sort of giving sort of a heuristic that says, well, if it's sort of near 50%, you know, maybe they have very accurate estimates of the percentages, and they're just saying, well, if it's sort of near 50%, that's more or less like equal. And maybe once we get to, you know, who knows? Why, I don't know why they're saying once we get to 53, then it makes sense to group it this one way versus this other way. Somebody had a comment here, Lisa.
Aren't there slightly more women in the world too?
There are slight, I think that's true, so that maybe has an effect on the right-hand column, right? I guess it probably wouldn't wouldn't necessarily be relevant for the percentages. Okay, other thoughts? Well, actually, let's go back to this question of what the people represent. I thought it was sort of confusing when I first looked at this that, you know, you realize after looking at, well, okay, the people represent these percentage points more than 50 or less than 50%, depending on which group you're in. But then they put the little person down here, which this I think is an absolute number of visitors, 99 million people. But then they have the person next to it, which made me think, well, maybe this is actually somehow in terms of absolute number of people. But then I was like, well, that can't make sense because, you know, these numbers and those align. So that was sort of something that had me confused to start with. Other thoughts? Yeah.
Well, I mean, the people graphic is kind of like the main thing that you're supposed to be looking at.
Uh-huh.
It's sort of misleading. Like, if you look at Instagram, there's 3 people, and Facebook has 8 people. So it looks like Facebook should have 3 times as many something as Instagram, but it's really only like a 5% difference.
Right. So yeah. So because they start the graph basically at 50%, we're often trying to interpret relative measures, but this is sort of mixing. This is sort of not a good way it makes it confusing if you're thinking this is relative measures. You know exactly what you said, that this is 58, this is 58%, and that's 53%, which is some difference, but it's not sort of the overwhelming 3 times difference if you try and interpret it on a sort of relative scale.
And the same thing kind of happens on there's some other like graphic on the far right that's supposed to show like, I guess the length of the line corresponds to the number in the second to rightmost column. But like Facebook and YouTube have way more visitors than everyone else, so like all the lines are really tiny except for like Facebook, YouTube, and like 2 other ones.
Right. So it's hard to see the relative comparison of some of these, you know, the less used websites because of the fact that we have these big outliers that overwhelm that aspect of the graph.
But even then, there doesn't seem to be like any actual, like, it seems to be like a relative scaling, but like is that 155 million for Facebook? I mean, that should be double the size of the YouTube one.
Yeah, I think this is probably just because I could blow it up more, but there's a little plus here that indicates this goes out here.
Okay.
Yeah. Okay, other comments? Yeah, Jeff.
Another thing they could have done is they could have put the 50% marker down the center and had, you know, one side and then the other sort of indicate the direction of the scale.
Okay, so your thought is that the graphic could look sort of like this, and then we'd have, for the women's one would be like this, and then you got down to here, and the men's one would look like this. Is that the idea?
Yeah, but hopefully they would have reversed the order of the women's scale, so you can see at the top are the ones with the...
Okay, so I think that's a really important point. Okay, so the first thing was, well, okay, rather than having us have to sort of switch our interpretation of what it means to go out to the right here, you know, when we switch from here to here, all of a sudden this means sort of more women, and then now this means more men. We sort of have to switch our understanding of what the percentages mean. So I think Jeff's first suggestion would address that if we had them going out from the 50%. Right? That might also help with that sort of relative thing of the 53 versus 58 that Alex was bringing up, I think, in some ways. But then you're saying the ordering, we could do a better job with the ordering. Right? So they've sort of done this weird ordering where they have equality first. It's sort of not clear why equality is first. And then they have, you know, then there's sort of a continuous scaling here from, well, I don't know whether there is or not. Do we know what the gray people mean? Do we know what the 51 and 52% mean? I don't know if that's more men and more women, because we know what it means here, we know what it means there. I don't think even if we looked at the legend down here that we even know whether the 51 or 52 is men.
The gray people, Foursquare are little men characters.
Oh, interesting. Okay.
But if this were printed in black and white, then really hard to see.
Okay. All right. So good catch. First of all, I hadn't that yeah. If you look very carefully, you can see these are the sort of stereotypical male and female figures in their suits and skirts. Okay. So presumably this means 52% men and 48% women. If you look very, very carefully, they're very, very discerning about this. So in fact, going from here to here is not even continuous because that's 52% men and this is 53% women. And then we increase to become predominantly women, and then all of a sudden we go back to the one that's somewhat more men, but not a lot more men. So we're sort of going middle of the road, extreme, middle of the road, extreme, which is sort of a weird way to put it. So I think, what Jeff was thinking, I guess, was that we would, I guess we might put the equality one as the bars here, and then we'd have Instagram, Facebook, blah, 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 up to Pinterest, and then going down this way we would have YouTube, LinkedIn, blah, 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 going down to whatever the most extreme men's one is, Reddit in this case. Okay, I mean, in some ways it's when you sort of see these graphics that are not in sort of formal reports or journal articles or things like this, it's sort of easy to pick on them and critique critique what they've done, but I do think it's useful for sort of drawing out what makes things unclear and what are some good principles in terms of scaling and putting things in order, like we were just talking about a second ago, making sure it's clear what the different symbols mean. And these same principles come up when you're doing more sort of serious analysis and data analysis and producing figures to accompany those sorts of data analyses. It's sort of more, in some ways, maybe it's more fun to look at these sort of graphics to make that point. But anything else that popped out at people? Yeah, Dustin?
I'm also not really a fan of using the proportions because if you just look at the two graphs and then you compare the female versus the men's, it looks like the proportions are about the same. And then they're
Wait, I didn't quite follow that.
For instance, if you just look, if you zoom out a little bit and you see the matriarchy and patriarchy side by side, you couldn't really tell that the matriarchy has all of that more visitors compared to the patriarchy just by those proportions.
Okay, so you're saying that you think it's interesting to see that you're saying the 99 million difference is interesting and it's not obvious from the overall graph.
And it seems largely skewed because Facebook is taking all the female visitors, whereas that's where the total is coming from.
Right. So a lot, yeah. So this is also sort of a story in when you're sort of averaging, or in this case summing, the big observations make the outlying observations like Facebook in terms of being so much more traffic than most of the rest of these make a really big difference in terms of the overall numbers. But yeah, I guess sort of another thing to riff on of what you were saying is, it seems like the main point of the graphic and where most of the space is taken up is here in terms of the proportional visiting. So it does seem like they sort of intended this to be mainly about the proportions rather than the absolute numbers, but it is interesting that they also tried to get the absolute numbers in there as well. And it's not completely clear to me why they did that, although I guess they just wanted to get sort of more information in here, which is in general often a good principle, is to try and get one of the principles that people talk about in terms of graphics is having a high ratio of information in a graph, a high ratio of having whatever ink you put into the graph provides a lot of information. Okay, so let's quit there. We'll see a few more examples from more sort of academic context, and then I'll talk some about some graphics in R on Friday.
Can I ask you a question on problem 4?